Okay, so let me go through it with you a little bit here in this video. Give me a second. I'm just going to set up a little bit. I've got to get my colors here. Let's see. Sorry, give me a second. I've got to get my colors. There we go. All right. Okay. So I'm going to start with the equation that we want to solve. And so that's K and D squared U dx squared minus U, and then equals partial U, partial T, and K is given as greater than 0. All right, I got to fix my pen. It's a little too thick. So give me a minute here. I'm going to fix my pen. Push palette. And of course, it's on the other screen. So, and let's put it down here. And let me see if I can fix it. It's a little thick. It's also on the other screen. So give me a second. Okay. All right. So let's start with the separable solution as usual, right? So we're going to have U equal X, and I'm going to color code here. Let's see, X of X and Y of Y. Okay. And so we're going to substitute that in and just go through the algebra. Okay, so we have K. And then when we take this second derivative of X times Y, notice that we're only taking, I know that you probably know all this, but I'm just going slow. So we're only taking the derivative with respect to X. So I can make this a full derivative, not a partial. So right now it's a partial, or it should be a partial. And so I could write this as Y just comes right out of the integral. We don't care about Y. And then this is going to be partial squared, or sorry, regular derivative squared of X with respect to X. Sorry, regular derivative. Okay. And then we have minus XY, right? Here for U, right? That's our guy. And then we have equal on the other side to a full time derivative times the X variable, because the X variable doesn't have any time in it, and we can make it a regular old derivative. So dy. Oh, you know what? My bad here. I totally screwed this up. Can we back up a little? So it shouldn't have been Y of Y. Maybe I should just call this really should be T of T. My bad. I for some reason was like thinking this was an X and Y, but it's T of T. Okay, there you go. Okay, so we'll just go back and erase. There we go. T and a T here. And you're probably wondering what was going on. Okay, so this is going to be big dt and then d little t. Okay, the big T, d little t. Okay, fine. Now we can divide through by u, which is xt, right? And so on this side here, we're just going to get a 1 over x because the t's will cancel, right? So we're going to get this k, and then we're going to get 1 over x. So I'll put over x. And then we're going to have d squared, dx squared of course, x. And then when we divide here, we're just going to have a 1. So minus 1. And then over here, right? So this is equal. And over here, we're going to have a 1 over t because the x cancels. Okay, so we get on this side, we get a 1 over t. And then we get d dt of big T. All right. Okay, again, we are separating the equation, right? So here we can say we have 2 halves. We have 1 half that's here. I'll type down in yellow. And 1 half that's here. And each of these have to be equal to the same constant. We're going to set it to minus lambda, which is what everybody seems to use, right? In the book anyway. So we're going to say each side is minus lambda. So let's set up our 2 equations then. we're gonna have, and now I'm gonna use the color coding that goes with the variable. So for instance, this is gonna be K over X, D squared X, dx squared minus 1 equals minus lambda. And then this one here is going to be 1 over t dt d little t is equal to minus lambda. Okay, so now we have two equations to solve. All right, so when I was talking about carrying k through, we're just going to sort of carry it through. Okay, so meaning we're not going to do anything with it. We're just carrying it through as we work through the problem. Okay, now, so I have two equations. Now, the first thing I'm going to do is I'm going to look at the conditions, right? There are three conditions. So first of all, I'm going to kind of mush my equations around so they look a little bit more like what I want them to look like. And so I'm going to get a new layer and keep going. Okay, so my first equation was K, that's in this color. So K over X. I'm just rewriting D squared X, D little x squared, and then minus 1 equal minus lambda. And the second equation was 1 over t d big T d little t is equal to minus lambda. All right, so now I'm going to put this in a different form by just moving constants around. Okay, so first of all, I'm going to get that 1 on the other side. So I'm going to have K, oh, wrong color, K over X, and then D squared X dx squared, and then equals minus lambda plus 1, right? Okay. Yeah, we have just a slight problem with K. So this is the issue with this particular solution is, and it's not really the solution, it's WebAssign. So when WebAssign is giving you conditions, it looks like it's not quite doing the right thing. So let me, oops, I just stopped share, which is not what I meant to do. In 1 second, I'll be right back. Okay, I'm back. All right. So at this point, right, you see we have this sort of pesky K here. And if we divide by K, so what I'm going to do, I'm going to say, where are my colors? There we are. So I'm going to divide by K on this equation here, right? And so here we go. I'm going to go 1 over, that's going to give me 1 over X, D squared big X, D little x squared, and then equals minus lambda over K plus 1 over K. Okay, now if we look at WebAssign, which I can't share with you right now, but if you go look at problem 2, right, in the chapter 12 homework, what you're going to see is that the conditions they're putting forth in this case are that, right, so the first condition is didn't mean to write on my colors, lambda minus 1 over K equals 0, right? And let's do that in different colors so we like keep our colors for the different conditions. So lambda minus 1 over K equals 0, right? That's their first condition, but I don't really have lambda minus 1 over K. Even if I multiply by a minus sign, which would give me lambda over K minus 1 over K, that's still not lambda minus 1 over K. This tells me that I haven't dealt with the constants the way that WebAssign wants me to get the right answer according to them, okay? So there's nothing wrong with what we've done so far. It's just that now I don't have their condition. Okay, so I'm going to back up to my previous slide, okay? So I got to go back and be like, okay, wait. I've got to divide by K at this stage. I'm going to divide by K at this stage, okay? So that I can have something that looks more like their condition on the right-hand side. All right, so I'm going to divide by K here, and I'm just going to do that by erasing and keep it in pink to see what's going on, okay? To show you what's happening. So we have here, this is going to be a 1 over that, and then I'm going to get a 1 over K here, and I'll get a K here, right? If I divide both sides of the equation by 1 over K. Okay, now when we separate, this is going to be 1 over K, and this is going to be 1 over KT, right? Okay, good. So now we're in sync with WebAssign, all right? So that K is a constant, and there's kind of no reason there's no rhyme or reason as to why you would do it this way. The answers are going to end up being within K, okay? So this is kind of confusing. But one thing you can do to kind of avoid this problem is to always put it in put the equation in standard form. Standard form would be having this thing with the coefficient of 1. So this K would have to be divided through for everybody, right? So we would have been like, okay, goodbye. You're gonna put K down here, and I'm gonna put a 1 over K here to start. And now I'm gonna start. Okay, putting it in standard form where you have a 1 for a coefficient for the highest derivative probably avoids all of this problem. That's not something I usually do, but okay. Okay, so now we're back to where we want to be. I'll just follow through here and just erase and put the K where I want it to be for K over K. Okay, so now everything's consistent, and we'll go back to our other slide where we continued to work. Where is that slide? There it is. Okay, so now I have the wrong one here, and I'm gonna go back and fix, right? So here, remember we had, oops, I got a memory layer. So we had here, this was just gonna be, I'm gonna fix here, so I'll keep everything in pink. Remember there was a 1 over K here, and there was a 1 over K here, and the lambda doesn't get the K because I divided before I separated. Okay, and so now here, again, I don't have the K, okay? And here I do have the K. Now, I'm gonna erase this one altogether. Now I'm gonna multiply this equation by a minus sign. So what do I get? And I'm go back to color coding. I get minus 1 over X, D squared big X, D little x squared is equal to lambda minus 1 over K. And now I'm in business, right? Because lambda minus 1 over K in our first case is 0. So I'll keep pink for our first case, and this becomes minus 1 over X, D squared big X, dx x squared is equal to 0. This is case 1, right? Lambda minus 1 over K equals 0, right? Okay, so that equation is easy to solve, right, by separation and just integration. So the first time I integrate, so this basically I multiply both sides by X, and I can even do minus X, and I end up with just this equation, D squared big X, D little x squared equals 0. Integrate one time to get dx d little x is equal to x, and then plus a constant. I'm going to call that a1. Integrate one more time, d big x dx is equal to x times a2. Sorry, my bad. My bad. Okay. And so, oh, sorry, I am messing up right and left. I am messing up. Okay. So integrate one time, this gives me a constant, not x. So I'll call that a1. Integrate again, constant times x now, plus a2. Yeah? Okay. So if this is too fast, write it down. See, I made a mistake by going too fast, so don't do that. Write down the integrals if this is confusing, right? Because I'm integrating this side here, right? I'm doing an integral of this, and the integral of 0 gives me a constant, right? And this gets rid of one of the derivatives, right? Remember, the integral is the antiderivative, right? So I'm integrating this dx and this dx, okay? So go through that if it's confusing. But anyway, that's the solution. My bad here. Sorry. X, that is the solution for big X. Okay, we have half the solution now. Let's go to our T in our pink case. So in the T, we have 1 over K T dt d little t is equal to minus lambda. Now, in this case, in the pink case, we know what lambda is, because if you notice, lambda minus 1 over K is 0. Therefore, lambda is 1 over K, right? So if I solve this for lambda, I get lambda equal 1 over K. So that's great. I'm just going to replace this with minus 1 over K. Okay, perfect. Now when I bring the K up there, it's going to disappear. So that's great. So I get 1 over T dt d little t. I'm multiplying through by K, and I get minus 1. All right. Separation to variables to integrate. So dt over dt is equal to minus t dt little over t minus equal minus t. And then as you know, this all integrates to t is equal to e to the minus little t. Right? Please prove that self. I'm going fast, I know. But if you integrate both sides, this, if you integrate this, right? And you integrate this. Oh, sorry, my bad. I forgot. So I'm trying to do this quickly, and that is not working out. So this should be like that. So if we integrate both sides, right? We get ln of t over here. Let me start that again, excuse me. Okay. dt over t is equal to minus little dt. Okay, that's much better. And then we integrate that. And this becomes ln of big T. This becomes t, or minus t, sorry, minus t. And then when we exponentiate both times, we get just t here and e to the minus t here. Okay, that is the solution for t. So the whole solution, right, is for the pink case, u is a1x plus a2, and then e to the minus 2. Okay. All right. So that's case 1. So let's get a new layer. So case 2, let's do in a blue. Okay. Let's write down our equations as we know them. So 1 over x d squared x dx squared is equal to, oh, there's minus, sorry, minus is equal to lambda minus 1 over k. That's our equation starting with starting, and we haven't said the case yet, but case 2 is lambda minus 1 over k is equal to minus alpha squared, which is less than 0, right? Okay, and then the t equation remains 1 over t, 1 over kt, sorry, 1 over kt dt d little t equal minus lambda. Okay, cool. Now, in this case, right, again, we're going to solve for lambda for this equation, but let's do this equation first. So I know that lambda minus k is this negative lambda squared, right? Okay, and so I have a negative sign and a negative sign here, which cancel out. So I get 1 over big X d squared big X dx squared is equal to alpha squared, right? And so let's solve this equation. I'm going to put it in a better form. So d squared x d little x squared is equal to alpha squared capital and then capital X. And I'm going to try for my solution e to the gamma x. So I don't know what gamma is. Whole point is here, I got to figure it out, right? Okay, so let's put that in here. So when I take the second derivative of this function, I get gamma squared e to the gamma x. And then on the other side, I have alpha squared e to the gamma x. I can get rid of these two. And then I have that gamma is equal to alpha. Well, plus or, my bad, plus or minus alpha. And alpha supposedly is real. Okay, so there's no i's in there, it's just a number. And so that means that I have the solution, right, for big X, something like e to the, well, you know, like some constant like a e to the e to the alpha x plus b e to the minus alpha x. Now, this is the solution. Now, WebAssign may not want that, right? So remember, when you have solutions like this, there are other ways to write it. So for instance, in this case, because this is real, right? These are actually real exponentials, right? A growing exponential and dying exponential. You can write this as sinh and cosh, okay? So, and in fact, that's what it wants. So different constants. So A1, sinh sinh of alpha x plus a2 cosh of alpha x. The solution actually tells me that it wants that. I don't know if it will actually accept just e to the alpha x plus another constant e to the minus alpha x, which is also, it's the same solution. It's just written differently. Okay, so we have x. Let's work on t. I'll get another layer. Okay. Okay, let's do it. All right, so we have 1 over k t dt d little t equals minus alpha. And we know that alpha, I said alpha, lambda minus 1 over k is equal to minus alpha squared, right? So if I solve for lambda here, I get lambda is equal to 1 over k minus alpha squared, right? Okay, great. So I'll just keep the lambda around. I mean, why not? I'm just going to keep it around. So I'm just going to keep it as a stand-in for this. That's okay when we solve the equation. So I'm going to put a rearrange. So 1 over t dt, and I'm going to put the lambda up here, minus k lambda. And then, of course, I'm doing my separation again. Dt over t is equal to minus k lambda little dt. Integrate both sides, and we get, after exponentiating, e is e to the minus k lambda t. And this is e to the minus k lambda, okay, t. And then the lambda is this. Okay, so we have 1 over k minus alpha squared, and just doing a little algebra, e to the minus, and then the k's cancel, e minus t, 1 minus k alpha squared. Okay, so there you go. That's t. All right, so you can put those two together, right? The x and the t. Okay. Okay. So, all right, the last case, this all runs really similarly. So let's do the last case. All right, last case we'll do in the sort of purple violet color. All right, so case 3. And case 3 is lambda minus 1 over k equal alpha squared, and this is greater than 0. Okay, so again, write our equations down. What do we have? We have 1 over x d squared big X d little x squared, and then we have equal minus, I keep forget the minus, lambda minus 1 over k, and now we can write that as alpha squared. Okay, and we're solving this one first. So I'm going to multiply through by this x, and multiply through by the minus sign as well. So d squared big X dx squared is equal to minus alpha squared x. Okay, again, I'm going to try a solution of x is e to the gamma x. And so second derivative gives me gamma squared e to the gamma x. And over here I get minus alpha squared e to the gamma x. We have a minus sign here. So when we cross those out, we get that gamma is equal to plus or minus I alpha. Okay, so this gives us solutions that look like this. X is a e to the I alpha x plus b e to the minus I alpha x. And again, you can write it any way you want. Now my solution here that tells me, WebAssign tells me what it wants. It wants in sines and cosines, which is perfectly reasonable, right? Okay. So I can rewrite this as two different constants, a1 times the sine of alpha x plus a2 times the cosine of alpha x. Okay, great. We've got that done. So let's go on to t. Okay. So this is case 3 again. And just to remind ourselves, that's lambda minus 1 over k equal alpha squared greater than 0. So what do we have? We have 1 over k t d big T dt is equal to minus lambda. And now we know, we can see lambda again is 1 over k plus alpha squared, right? And so let's keep the minus sign there, and we'll just write it in this time, okay? I hope you don't mind. So we're gonna have minus 1 over k plus alpha squared here. And let's separate out. I'm gonna pull the k up first. So I get 1 over t dt d little t is equal to minus. Now the k is gonna cancel this one. So we get minus 1. And then we get, sorry, well, I can pull the minus sign in, but you get 1, and then you get plus k alpha squared, okay? Plus k alpha squared. All right, cool. And now separate and integrate. T d over t is minus 1 plus k alpha squared, little dt. And there we go. After exponentiating, we get e to the minus 1 plus k alpha squared t. And there's our solution for t. I hope this helped. And I hope that, you know, all the mistakes I made didn't bother you. Okay, let me know what you think and make sure that this works for you. I've got to get my mouse and stop the recording. Sure. Give me a second here. Stop recording. Can't find the mouse. I'm working with 2 screens. Oh, there we go.